Good morning, dear students. We continue our geometric modeling course. The topic of this lecture is tree data structures and their applications. The picture shows a scene from a ballet of the Netherlands dance theater where a tree is hanging from the ceiling. What is interesting is that tree structures in computing are usually drawn this way with the root at the top and leaves at the bottom. First, I will illustrate using tree structures in the daily life. Then we need to define the notion of a tree data structure in computing, learn its terminology and processing. Applications and implementation of trees on computers will be given a special attention. Let me remind you that a circuit in a graph is a path that starts and ends on the same vertex. A tree is a connected undirected graph with no circuits. A tree is a connected graph with n vertices and n-1 edges. A tree is a graph such that there is a unique simple path between any pairs of vertices. All of above say the same thing. An example of a tree structure is shown below. It has no circuits indeed, but it's useful to see what graphs are not trees. Two structures at the left are not trees, because they have circuits. The structures at the right is a correct tree. With the above definition, it's easy to point out the correct trees in this figure. A and C items are trees, but B is not a tree because of circuits. A non-trivial question is how many different trees exist for the given numbers of nodes n. As you can see on the slide, for n between 1 and 3, there is only one valid tree. Two different trees exist with 4 nodes and 3 trees can be built with 5 nodes. A rooted tree has one vertex designated as the root, and every other edge is directed away from the root. We usually put the root at the top. A leaf node in a tree is any pendant or isolated vertex of degree 1. An internal node is any non-leaf vertex. The selection of the root is arbitrary. The same tree structure produces different rooted trees as shown in the figure. A given unrooted tree with n nodes results in n different rooted trees. Let's consider tree terminology. Now several useful definitions for the tree terminology. We have just seen examples of all of these terms. Parent node is adjacent to the child node and replaces above it in the rooted tree. The ancestors of a non-root vertex are all the vertices in the path from root to this vertex. The root has no ancestors. The descendants of vertex v are all the vertices that have v as an ancestor. Leaf nodes have no children. Sibling nodes have the same parent. Node with children is an internal node. The level of vertex v in a rooted tree is the length of the unique path from the root to v. The height of a rooted tree is the maximum of the levels of its vertices. For example, the height of the genealogy tree is the number of generations between the root and the youngest descendant. The subtree at vertex v is a subgraph of the tree consisting of the vertex v and its descendants, and all edges incident to these descendants. Let's look at an example of a company's tree structure in the next few slides. This is tree root. It has no ancestors. These are leaf nodes. Leaf nodes have no children. Our tree has levels. Level of vertex v in a rooted tree is the length of the unique path from the root to vertex v. The zero level is highlighted on this slide. This is the first level of tree. This is second level of tree. These are sibling nodes. They have the same parent. These are sibling nodes too. As already said, subtree is a subgraph of the tree consisting of a vertex and its descendants. The left subtree is highlighted on this slide. The right subtree is highlighted on this slide. There are many notions related to the tree structures. First, we will try to grasp them by example, and then we will give more formal definitions. In the shown tree, the parent of H is B. C is a child of K. The ancestors of I are E, K, and A. The descendants of B are F, H, and D. A is a root and has no ancestors. K and its descendants make a subtree. The sibling of G is J. The leaf nodes have no children: F, D, J, G, and I. A not necessarily connected undirected graph without simple circuits is called a forest. You can think of it as a set of trees having disjoint sets of nodes. Now let's consider n-ary and binary trees. A rooted tree is called n-ary if every vertex has no more than n children. It's called full if every internal non-leaf vertex has exactly n children. A two-ary tree is called a binary tree. These are useful for describing sequences of yes-no decisions in the form of a decision tree. The tree is called a full binary tree if every internal vertex has exactly two children. A given rooted tree is a binary tree if every node has degree less than or equal to 3, and the root has degree less than or equal to 2. With this definition, which tree is binary on this slide? An ordered rooted tree is just a rooted tree in which the children of each internal node are ordered. In ordered binary trees, we can define left child, right child, left subtree, and right subtree. In the shown example, left subtree consists of the node B and its descendants. Right subtree consists of the node K and its descendants. A rooted binary tree of height h is called balanced if all its leaves are at levels h or h-1. Let's consider binary tree properties. A tree with n vertices has n-1 edges. There are at most 2 power h leaves in a binary tree of height h. If a binary tree with L leaves is full and balanced, then its height can be calculated as following. Now let's consider the computer representation of trees. How do we effectively represent a tree in the computer? A binary tree data structure with attributes is usually used. It has 3 fields. Data field holds the actual information in a node. Left field points to the binary subtree to the left of the current node, or is empty. Right field points to the binary subtree to the right of the current node, or is empty. The binary tree data structure can be represented in the computer by a shown table. Each row of the table corresponds to a node with the same number. The column data here only shows the node number, but it can be any other useful information. The column left is a number of the left child. For example, 2 in the first row means the node 2 is the left child of the node 1, which is the root. The column right is a number of the right child. It's 11 for the root. Another compact representation of a tree is a one-dimensional array, when we set parent for every node. Now let's consider tree traversal. If you have got some discrete structure, one of the first things you want to be able to do is traverse it. The traversal means a walk along the tree with the purpose of visiting all its nodes. A traversal algorithm is a procedure for systematically visiting every vertex of an ordered binary tree. Three traversals are defined recursively. Three traversals are named preorder, inorder, and postorder. This is preorder traversal algorithm. Let T be an ordered binary tree with root R. If T has only R, then R is the preorder traversal. Otherwise, suppose T1 and T2 are the left and right subtrees at R. The preorder traversal is following. Begins by visiting R, then traverses T1 in preorder, and traverses T2 in preorder. Here is an example of preorder traversal. The root is visited first, then visit left subtree, and visit right subtree last. The result of traversal is shown on the top of slide. The shown traversal is performed with a recursive preorder algorithm shown in the light green window. It starts with the root, visits all the nodes of the left subtree, and then the nodes of the right subtree. The order of visiting the nodes is shown at the lower left. Preorder is a recursive tree traversal function. This is Inorder Traversal algorithm. The main difference from Preorder Traversal algorithm is that we begin from traversal of the left subtree in Inorder, then root, and after that the right subtree. Here is an example of Inorder Traversal. The result of traversal is shown on the top of slide. The Postorder Traversal is following. We begin by traversing the left subtree, then right subtree, and end by visiting root of tree. Here is an example of Postorder Traversal. The result of traversal is shown on the top of slide. Now let's consider binary expression tree. One of the widely used forms of tree in computing is a binary expression tree. It's applied in compilers and interpreters for representing and calculation of arithmetic and other expressions. This is a special kind of binary tree in which each leaf node contains a single operand, such as a number or a numerical variable. Each internal node contains a single binary operator, such as summation or multiplication. The left and right subtrees of an operator node represent sub-expressions that must be evaluated before applying the operator at the root of the subtree. You can see the variants of the binary expression tree traversal on this slide. It's inorder, preorder, and postorder traversals. When a binary expression tree is used to represent an expression, the levels of the nodes in the tree indicate their relative precedence of evaluation. Operations at higher levels of the tree are evaluated later than those below them. The operation at the root is always the last operation performed. There are infix, postfix, and prefix notations for writing expressions. When we use infix notation, the operators are written in between their operands. This notation is produced by Inorder Traversal. In case of postfix notation, the operators are written after their operands. The postorder traversal is used for producing the postfix notation. And in case of prefix notation, operators are written before their operands. This notation is produced by preorder traversal. This is example of the binary expression tree with different traversals with producing infix, prefix, and postfix notations. The order of the tree traversal for a more complex expression is shown in blue. The actual order of the evaluation is shown below. The summation operation is calculated first because it first gets both of its operands. Infix notation is easy to read for human, but hard to evaluate for computers. Prefix notation is complex to evaluate for computers too. So computers evaluate expressions using postfix notation. This special binary tree structure is called a cut tree.